What's up, y'all? This is just a quick video to discuss some vintage paleo art by an artist named William D. Berry that have been making the rounds in the online paleo art community. William Berry was active as a paleo artist from the 40s to the 60s, and these pieces have been going around and getting a lot of praise for being years ahead of their time. One artist even went so far as to say that they look contemporary. But is that really true? How far ahead of his time was William Berry? And what can the recent resurgence in popularity of these pieces tell us about the broader relationship between scientific paleo art, pop culture, and our perceptions about dinosaurs? Specifically, the scene shows an Allosaurus chasing some kind of an ornithischian dinosaur in a Morrison formation, sort of a typical Morrison formation paleo environment. What I'm going to do in this video is analyze this artwork from the perspective of a paleo artist that's been working with paleontologists on Morrison formation dinosaurs for the last 5 years. Of course, people want me to comment on the theropod because that's what everybody's interested in. So I'm going to actually get to theropod last. I'm going to go from the environment forward. This actually isn't a terrible reconstruction of the Morrison paleo environment, but it's pretty basic in that it's a very broad brush stroke reconstruction of the plant life and surrounding landscape. And I mean that literally broad brushstroke, but also figuratively. I mean, it's kind of unclear what this plant material in the background even is. I mean, grass hasn't evolved yet, so maybe that's supposed to be horsetails like these ones in the foreground. But overall, this reconstruction of the environment is typical of Morrison formation scenes where the plant life and surrounding ecology gets very little attention. And that's unfortunate because that lack of attention on the plant life in the Morrison has created a lot of persistent misconceptions about the Morrison paleoecology and climate that persist to this day. And we're only just now starting to make some really interesting discoveries about the plant life and ecology of the Morrison, which we'll actually be covering in upcoming installments of my documentary Jurassic Reimagined. So moving from the surrounding environment up the food chain to the herbivore, we have some kind of ornithischian dinosaur. This reconstruction isn't clearly anything that we have in the Morrison. It's kind of Dryosaurus sized, but the skull shape is totally wrong for Dryosaurus or for Camptosaurus. I guess it could be passed off as a baby Camptosaurus, but a bunch of the body proportions are wrong. Camptosaurus have these really enlarged ilia on their pelvis. They would have had really big back ends. The overall skull shape is a bit off for Camptosaurus. It kind of looks like an iguanodon. Okay, quick note to insert here. Tyler Greenfield notes that what William Berry may have been trying to depict was an animal we now call Eutheodon, which used to be considered a kind of Camptosaurus, but they had put a skull from an early Cretaceous iguanodontian on it. So if you look at it from that perspective, yeah, it's a little more accurate for the time. It certainly isn't updated to our modern understanding of these ornithischian dinosaurs, as the most recent understanding of these animals was sorted out in 2011 by one of my collaborators, Andrew McDonald. I'm including links to the papers chronicling the saga of Eutheodon in the description of this video if you want to go down that historical paleontology rabbit hole. I'm actually going to read a passage from one of these papers because it gives a really great sense of how messy the early days of paleontology were, especially in the Bone Wars era. In 1878, I discovered in one of the ridges east of the Red Rocks, forming the east boundary of the Garden of the Gods, portions of 21 sea monsters that had been caught as in a basin in one of Earth's early paroxysms. There were many vertebrae of large size. Some of them were well preserved. Of the large animal in the form of a saurian, we could only find casts of parts. From the lay of these parts, we calculated that the animal was 117 feet in length. Most of the bones and some of the casts were boxed up for Colorado College. The college at that time having no place to store such things, the boxes were placed in barns and cellars, and nearly all have been lost. So the Allosaurus also has some pretty major issues. This wide, short skull looks to me to be clearly based on the American Museum of Natural History Allosaurus mount from 1908. Edward Drinker Cope found an Allosaurus skeleton. It had a partial skull, and they sculpted the rest of its skull. What they sculpted looks just like this short, wide skull, which isn't accurate. Another quick aside here, Tyler Greenfield on Twitter noted that in William Berry's reconstruction, he has a ridge running along the nasal bones of the Allosaurus. That ridge is not preserved in the American Museum specimen, but it is preserved in the Smithsonian specimen from the same era. The Smithsonian specimen was found by Marsh, Cope's rival, and like the one that Cope found, the skull was highly fragmentary. So the people at the Smithsonian sculpted it back together, and again, they made it too short and too wide. William Berry may have been looking at both specimens. I'm including a link to Ben Miller's blog, Extinct Monsters, which chronicles the history of the Marsh specimens at the Smithsonian, so you can check that out. Ultimately, though, this doesn't really change our interpretation of the skull being kind of the wrong shape and not even really being up to date for the middle of the century when William Berry was working, because this beautiful, nearly complete skull was found at Dinosaur National Monument in 1924. We now know that they have a much narrower skull, it's a bit longer, and the horns on the frontals and lacrimals that make these crests on Allosaurus are much more exaggerated in the well-preserved skulls. And on top of the bony crenulations and knobs and lacrimal horns, we would expect some type of a keratinous covering. That would have enlarged these horns substantially. We don't know exactly how much, but it's probable that there was a lot of individual variation. And so overall, the skull shape is a bit wrong. It's also an interesting detail that the artist included an alligator-like tongue, basically a very reduced tongue. The teeth seem to protrude directly from the gum line without really any lip material. The tongue especially is unlikely, as the strange flap-like tongues of crocodilians are a derived trait that they evolved when they took on a semi-aquatic lifestyle. Those flattened tongues form a flap in the back of their throat that keeps water from sloshing down their throat when they're eating things in the water. The null hypothesis for dinosaur tongues would be that they had tongues something like a tuatara, kind of your basic fleshy reptilian tongue. Tuataras are these lizard-like things that live in New Zealand. Allosaurus is much closer to the bird part of the reptile tree than tuataras, and it's a really evolved super predator. It's an apex predator. It's got a bunch of adaptations for that lifestyle. I would be willing to speculate, and I think a lot of paleontologists would support this, that these things probably had a tongue somewhat like a modern bird of prey, or something with keratinous spines or hooks on it, something to actually increase the friction on the tongue so they can actually pull meat into their mouth. We see that kind of an adaptation in a number of modern predators. Another detail that isn't contemporary at all is the neck length. Allosauruses have surprisingly long necks. Their neck is just about as long as their rib cage. One of the things that this almost gets right is the hand position. The Allosaurus's hands are in more of like a clapping position. They're not pronated with palms down, like what we would call bunny hands. But there's still some issues with them. The muscular reconstruction really looks like a lizard, and the claws are way too small, even if you were just illustrating the bone core of the claw, the bony center of the claw that's preserved in the fossil record. These claws are too small even for that. But we know from studying modern birds that there were these really enlarged keratin sheaths on claws, especially claws used for prey capture. One of the other pieces that's presented with this is this reconstruction of the theropod forearm. And at first glance, it really looks cool. It looks believable and plausible. And this is actually a great example of how realistic looking art can be really deceiving. Because at first glance, it looks good, but when you look closer, there's some major issues with it. First of all, the biceps muscle should descend actually under the pectoralis muscle. The deltopectoral crest is this bump on the humerus that the deltoid muscle wraps around onto from the back, and the pectoralis muscle inserts into on the front. So the pectoralis pulls the arms closed, the deltoid pulls the arms back. It really looks like the bicep would interfere with the pectoralis muscle inserting into that deltopectoral crest. An even more glaring example of something that's kind of very wrong is that the triceps longus muscle, a muscle that should attach at the elbow and go all the way up the scapula. It also looks like the scapula is at a funny angle in there. The triceps longus should attach to the elbow and go all the way up to the scapula. And that's the muscle that when it contracts, it makes the arm extend. That muscle group is completely missing in this muscle reconstruction. So the head is from 1908. The neck is verifiably way too short. And then when we get to the back end, it's a whole big, huge mess. There's some going on with the thigh here. There's like a butt above the thigh with this weird constriction here, that makes basically no sense. It looks like he was trying to blend some kind of crocodilian features, but hadn't been all that rigorous in that reconstruction. So I'm going to actually explain what we now think, what the current thinking is on how the hind limb musculature of theropod dinosaurs worked based on birds and crocodilians. Okay, so what we have here is a sketch of the bones of the rear end of Allosaurus. The tail is going this way, and I haven't drawn the whole tail here because I wanted to show the pelvis from the front view. This is the pelvis, the leg, and some of the rib cage sketched in pretty loosely. Now, a lot of people ask me when I'm doing science communication stuff, what are these bones hanging down here from the pelvis? Little boys always make jokes about these bones. In reality, these bones are really important to our understanding of how the theropod hind limb works. This is the ischia. There's two bones that kind of come together in the back called the ischia, and this is the pubes, and it's two bones in the front that come together. Now you'll notice that they come together almost as low as the knee, and they're spread pretty far apart, and there's a reason for that. These bones are muscle attachment points for an important group of muscles that keep the legs pulled together towards the midline. Now, in modern birds, the pubes and ischia have both swung way back, and birds hold their femur in what anatomists call a subhorizontal position. Their femur is up here, and it doesn't move very much when they're running. They mostly run by kicking out their tibiotarsus, their tibia and fibula, that have kind of fused together in birds. So birds have this funny way of running where they're not moving their femur very much, but they're kind of kicking out their knees. And the reason for that is because they've lost their long tail and put a whole bunch of muscle on their front end for their big wing muscles. The long tail in Allosaurus is another really important muscle attachment point. There's huge muscles that run down the tail called the M-cauda-femoralis longus muscles that insert into the femur here and pull the femur back in order to make the leg pull back and drive the animal forward. In crocodilians and in birds, the whole surface of these bones hanging down is clothed in muscle that attach to the inside of the leg. On the ischia, there's a group of muscles called the ischiotibialis muscles that connect down to the inside of the tibia. There's also the pubo-ischiotibialis muscles and something called the ambiens. Altogether, this group of muscles constrains the movement of the leg. They hold the leg in toward the midline, and they would connect all along here. So in a lot of paleoart, you see the pubic bone and the ischium sticking way down out of the belly of the animal. That's not actually accurate. We know from studies, dissections of crocodilians and birds, that this whole area would have been filled up with this mass of really important muscles that would have held that femur close to the body. Without these muscles, when this big long animal turned, they could easily dislocate their hip or do the splits. And that would be bad if you're trying to run down prey, as in the paleoart that we've been discussing. Now, as I mentioned, there's another big important group of muscles connected to the tail. That's the M-cauda-femoralis longus group, and it inserts into this lump on the back of the femur called the fourth trochanter. And people who study these muscles in crocodiles find that in crocodiles who move around with their tail, the M-cauda-femoralis longus muscle is huge, and it fills this whole area under the tail. On top of that, there's muscles that attach to the spinous processes on top of the tail, and those are necessary for stiffening the tail so that when this giant M-cauda-femoralis longus muscle fires, the tail is held straight, and the thing that gets pulled back is the femur. These muscles actually go over the M-cauda-femoralis longus and completely turn this tail into a giant mass of meat. I've been talking a lot about this with Oliver Demuth, and his feeling is that when you reconstruct dinosaur tails, you should basically just draw two straight lines from the ischium and the ilium. This is the top of the pelvis, or the top of the muscles that would have covered the top of the tail. Just basically draw a straight line back to the end of the tail. It should be about that massive based on what we know about the musculature of modern crocodilians. Now, That's only part of the musculature. So we've reconstructed the inside of the leg, sort of the groin region, but now we need the muscles that pull the leg, kind of stabilize it, and also help to pull it up and move the tibia around. And so we have the iliotibialis muscle group, this massive muscle group that attaches to the ilium and comes down and attaches at various points on the tibia. This muscle group is big, chunky thigh muscles that fill this whole area in. And we would expect them to just completely fill up this whole zone. Now, wrapping around this in various ways, there's the muscles of the calf. I'm not going to get into reconstructing each one of these muscles in detail, but we can get a general sense of their mass by looking at things like ratite birds and chickens, birds that are running around similar to theropods on their back legs. The difference being that theropods have this really long femur that swings back and forth, whereas birds tend to have a shorter femur that doesn't swing very much at all, and they have a long tibiotarsus, so the shin bone is a lot longer in birds, and the metatarsals are a lot longer in birds. So these muscle groups would have tendons that run down the foot. There'd be some small stabilizing muscles in the foot, and then we'd have a soft tissue envelope around this foot, giving it a lot of padding. We know from footprints that these things had a lot of padding around their feet. So when we start to reconstruct this and really fill all these spaces in, we end up with a really chunky back end without a lot of space in between the legs. So if I draw in the iliotibialis muscles here, filling all this area in, and then we know from crocodiles and birds that there'd be all of these back muscles completely engulfing the ilium and the spinous processes coming out of the vertebrae. Now, in the case of dinosaurs and crocodilians, those muscles engulfing the spinous processes on the tail actually go a little bit above the spinous processes, and there's usually a big ligament that connects all of those. Ligaments are the rubber bandy connective tissue that connect the bone. We would expect something similar along the back of bipedal theropods as well. Will hold up their whole front end, and big ligaments again connecting these spinous processes. Now, along the belly, there's these small ribs called gastralia, and what these ribs are actually ossified ab muscles. So these dinosaurs would have had this massive ab muscles connecting to the pubes here, and those muscles were they needed to be so stiff in order to keep the animal's body from bending too much here that they actually got reinforced with calcification. They developed little ribs in there. And then this whole body cavity would just be completely sheathed in muscle. If we drew in the scapula here, this whole area would be buried in muscle. You would not see the scapula at the surface at all. So when we reconstruct this animal according to what we know from birds and crocodiles, it ends up looking a lot like a really chunky bird with a really fat tail down the back. So if the specific details of William Berry's reconstructions here don't quite hold up to our modern understanding of these animals, why does it look so lifelike and realistic? I mean, it definitely looks more believable than a lot of paleoart from the middle part of the 20th century. I think that's because William Berry wasn't just a paleoartist. He was a wildlife artist. He spent years in the wilderness of North America sketching and drawing and painting real, modern, living animals from life. In many ways, he was an observational biologist who recorded his observations and communicated his understandings through art. That visceral sense, that visceral, instinctual, deep understanding of how animals work imbues his paleoart, giving it a lifelike character and believability that is indeed years ahead of its time. Where this art falls down is in the specific details of the reconstruction, which I think are influenced by a bias in paleontology that goes all the way back to the early years of paleontology. See, back in the late 1800s, Sir Richard Owen coined the term Dinosauria, which means terrible reptile. And he really promoted this primeval, reptilian, lizard-like view of dinosaurs. Now, it's important to bear in mind that in these early days of paleontology, there was a lot people didn't understand. These scientists were grappling with these new concepts of evolution and geology and ecology, but they were still traditional-minded Europeans with kind of a colonial and biblical worldview that influenced and pulled and tugged their perception of the natural world. Sir Richard Owen really viewed dinosaurs as these antediluvian, primitive reptilian behemoths. But Sir Richard Owen wasn't without his critics. In 1868, just a few years before Cope and Marsh would embark on their famous bone wars trying to dig up dinosaurs in the American West, Thomas Henry Huxley proposed that Archaeopteryx, which had been discovered in Germany, was a bird-like theropod dinosaur. And he proposed that birds evolved from theropods all the way back in 1868. So why did it take so long for the rest of paleontology to catch up with what Thomas Henry Huxley figured out in 1868? I think it's because his rival, Sir Richard Owen, created the more powerful paleoart. In 1852, the Crystal Palace dinosaurs were constructed, and these massive sculptures cemented in the popular consciousness the idea of the antediluvian primordial behemoth reptile view of dinosaurs. And I think subsequent generations of paleoartists have been gradually shedding the vestiges of these antiquated views all the way up to William Barry's time. We're only just now emerging from the Sir Richard Owen era of paleoart that viewed dinosaurs as terrible reptiles. We're finally starting to see them as the ancestral tree that gave rise to birds. I think when we analyze this paleoart from that historical perspective, it gives us some really important takeaways, especially those of us who make paleoart in our modern era. Very often, the reconstruction that's most similar to what everybody else is doing is viewed as the safer or more conservative reconstruction. But I don't really think that actually is the safer reconstruction. If we look at William Barry's artwork, where it holds up is in that it depicts Allosaurus as an active, muscular hunter in a complex ecology chasing down its prey. Those aspects of the art do hold up. The specific details of the anatomical reconstruction, I think, are vestiges of that archaic reptilian view of dinosaurs. The things that hold up best in the long term aren't the things that are clinging to past reconstructions, but rather the details that are drawn from strong observational biology, whether that's from observing modern animals or from thorough research of the fossil record, as Thomas Henry Huxley did in 1868, when he recognized the theropod bird connection about 100 years before anybody else would try and restate that argument. I think another reason William Barry's artwork looks ahead of its time is because when we think about paleoart from a given era, we very often think of pop culture depictions of dinosaurs and other prehistoric creatures from that time period. When William Barry was working in the 50s and 60s, movies featured amazing stop-motion animated dinosaurs by Ray Harryhausen, which were actually based on the scientific paleoart from a generation before, when Zdenek Burian and Charles Knight were depicting dinosaurs based on stuff being found in the Bone Wars. And I think that illustrates an important point, which is that pop culture paleoart is very often 20 to 30 years behind the cutting edge of scientific paleoart, which is what William Barry was creating in the 50s and 60s. I think we can actually close that gap between pop culture paleoart and cutting edge scientific paleoart. But part of the process of closing that gap is actually being willing to depict the latest hypotheses, and also encouraging artists to do that rather than immediately criticizing people for creating depictions of prehistoric animals that might not look like what people expect to see. So I encourage all paleoartists to be willing to speculate and do reconstructions of the latest hypotheses if indeed They are based in a strong observational biology. And I encourage all critics of paleoartists to hold back until you've really looked into the research that's going into their artwork, and maybe give the artist a chance to express what their goals are in creating the art before you pass judgment on it. I often see people criticize paleoart that's not meant to be scientific, as though it is supposed to be scientific art, and I don't think that benefits anybody either. I think there's room in the world for fun, ridiculous depictions of totally fictional animals, as well as paleoart based on the latest cutting-edge science. We live in an amazing time where artists have access to incredible resources that would have been hard for somebody like William Barry to get a hold of. I think if we can encourage artists to depict new stuff, that actually feeds back into the science, because it inspires paleontologists sometimes to look at the data in new ways, and it can also help paleontologists to communicate new hypotheses in a more compelling and powerful way. Maybe if Thomas Henry Huxley had an amazing paleoartist depicting a really believable reconstruction of bird-like dinosaurs back in the 1860s, our paleoart and our science might actually be years ahead of where it is now. I hope you enjoyed this video. If you did, let me know with a comment below, or if you have any other questions, I'll try and answer any of those that you may have. I'm also putting links to a bunch of really interesting scientific resources in the description of this video, so you can check those out if you really want to go down the rabbit hole and get a deeper understanding of some of the historical paleontology and some of the actual anatomy and modern paleontology that went into this video. Thank you all for watching. Have a great day, and if you're a paleoartist, don't be afraid to speculate and create reconstructions based on the latest science.